Last time we talked about operators. There's another video I put together about operators. Here I'm talking today about a what they call a outer product or an outer product operator in quantum mechanics. Now, as I said in other videos, the this ket, this notation, this representation, the ket is nothing but a column vector. And it can be a column vector of three or more, or two elements. Um, I just so happen to use uh, three elements for a column vector. So this whole thing, what is an outer product and how is it an operator? Well, we did. I said last time on the video about operators that they are matrices. They're basically matrices. So today I'm gonna quickly show that yeah, well, it's a matrices is operating on the outer product is operating on a column vector or a ket, and you get another ket or another state if you're talking quantum mechanics. So pretty much you kind of see the layout because it's already here. But just to give you an idea, an example, because a lot of this quantum mechanics is always seems to be abstract, which is nothing wrong with that because you need to be kind of abstract to kind of understand what's going on, but you also need to see how these mathematical or linear algebra type dynamics, how things calculate. As I always say, under the hood, how does this thing work? What does this thing look like with numbers when you do actual calculation, or instead of talking about abstractions? So if you're talking about describing an electron or some kind of elementary particle or some particle with some kind of potential, and you describe the system by um, uh, instead of a continuous way, but a discrete way, which what we have here, it tends to become a mathematical abstract. So you want to kind of get to physical because this is what it is. It's quantum mechanics. It's physics. So what we need to do here is let's just see how these kets behave. Here's the ket, but here's the broad version of this ket, and you can see that when you do a broad, it is actually a row vector. This is a little mistake here, but you can see how if you have a complex number, you take the complex conjugate. Now, they're orthonormal um, because you can see, well, they're not orthonormal. My mistake, they're not orthonormal, but that's a different subject. But if you put these broad kets together, you come up with an actual number. And so happen when you take this broad ket of the phi or this Greek letter, you put them together, you get 2. All right. So why am I doing that calculation? Well, the whole thing of this video is that I'm trying to figure out what in the world is this outer product, because you see in quantum mechanics, the outer product is an operator. Well, how is that an operator? Because I mean, I'm seeing these Greek letters and I'm not seeing uh, any numbers. What's going on here? Well, like I said, again, it's a matrix, and you're about to see that it is a matrix. Now, if we do the normal quantum mechanics, mathematical physics operation, and I operate here, I'm operating this outer product on this 3 times the uh, ket here. When I do that, this operates on that actually operates on this ket here. We already calculated this, which was equal to 2. It's equal to 2. But I put an extra step in here to show that this is a number, so this can be moved over to here. We have to be careful because we're dealing with matrices. Matrices or column vectors are not commutative automatically. So we have to be careful and be very strict with our linear algebra. But this all happens to be a number. So when that number is moved, this is right behind the 3. But we calculated this, and this was 2. So simply you multiply the simple math. You just multiply 3 times 2. This is 6. Now we already have this Greek letter phi. I get my Greek letters mixed up, but this is defined here. You see where this is defined: 4, negative I, complex number I, and then 2. And when you multiply them together, this is what you get. So I went through all that, you know, and in your normal way, you would do calculations. If you're studying quantum mechanics, you're doing you quickly go through this. This step here is what you quickly go through. You go through that, and you don't even you don't even think about it. What's under the hood? Okay, but what is this really? So I said it was a matrix, and I'm gonna show that it is a matrix quickly. And what I do is I'll take the two uh, cats here, but I only need to make this into a bra. So which I'll make that into a bra. Now normally I have a row vector and I have a column vector. So you're looking like, well, what this has to be, we go back to our linear algebra. Let me draw here. Our linear algebra, you got to be careful what you do because you can't multiply any two of matrices or column vectors because they have to match up. So this column vector has to be a 1 by 3 1. I think it's 3 by 1. So 3 by 1, 3 by 1, and then the other one has to be a 1 by 3. And this has to go into a 3 by 3. So this is why this is in this position, because you got to make a matrix. This is just basic linear algebra if you already know any linear algebra. Now if you don't know any linear algebra, this is definitely this is not going to be obvious to you. But that's what you need to do. That's what that outer product operator is. So when I do my matrix multiplication, you can see or multiply these two, this column vector with this row vector. You can see that I multiply each element here 4 times 1. That's the first element. 4 times 0. That's the first if we're talking about matrix, first row, second column. 4 times I, first row, third column. You do the same thing in the second row and the third row. So when I do the calculation, I get a 4, 0, 4i minus I, 0, 1, 2, 0, 2i. This is your outer product operator. Outer product operator. That's what it is. Okay, so what I did down here is for this video was to repeat what I did here, because this is the math you would do with quantum mechanics. That's the purpose of being abstract, because you don't want to go through all this math. But a lot of times students don't understand how to navigate. That's what makes quantum mechanics so difficult, because you're trying to understand the next step. How do you navigate in a mathematical abstract? And you're describing something that you can't see. You're describing, if you're trying to find out momentum, position, Any of these things. You're kind of in a sense blinded. Now we're talking physics. As opposed, you do a comparison classical mechanics. If you're trying to get the energy of the system, you're trying to calculate the kinetic energy and the potential. You can draw it out. Classical mechanics, you draw those things out. But in quantum mechanics, it doesn't work that way. You do things by probabilities. You do things, of course, you also have a potential, but you don't actually see the particle actually as it moves. You can describe where it's at, what types of states it's in, uh, and that 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 is when you have to uh, understand that you're just not going to physically see this uh, this small particle like electron or proton or some other small particle that you're dealing with. So this is what you deal with. Now, I digress a little bit. I'm getting back on subject. Okay, so what I did, you go back to here, you're trying to do this again, do this operation again. And we're doing it a different way. So we just take 3 times the column vector that is defined up here. And we operate it on that column vector. Well, we multiply a constant by the column vector, and of course you get 3 over 3, 0, and a negative 3i. That's what's here in the next line here. Now we take that operation, which is the matrix, and we just operate it on this state. Now we should be able to get the same result we got here, which was the column vector 24, negative 6i, and 12. Now I do that, and you see I multiply the matrix, which I say I defend that it's not operated by the column vector. I do the calculation because you got a 3 by 3 with a 3 by 1, and it has to be a 3 by 1. The same thing we got here. And I did the multiplication. You can look at it, check it out, look at the math, and I get 24 minus 6i. 24 and minus 6i and 12. Same thing I got here. So you see how this thing works. This is mathematical physics for quantum mechanics. So I just want to show what is the components of an outer product. What is an outer product? Seems to be a particular outer product because it's not. It's a matrix. It's a constant matrix. It's not any variable matrix or something like that, but it's a constant matrix. So I hope this helps. This short math demonstration. I hope it helps people that are students that are studying quantum mechanics. This is Alpha Mad Scientist. Please subscribe to my channel, like and share it so it can help other students. If you have any comments, leave comments. There's more to come, but I want to make sure these simple things. I know there are many advanced students, but students that are first studying quantum mechanics, it makes life easier when you start off very simple and simplistic. Because linear algebra, you taking linear algebra course is not gonna. The notation is different, and the notation be intimidating. And here the notation is it's no different from linear algebra. Don't let it intimidate you because it's not. It looks like Greek. That's what they literally say, and it does look like Greek, but do not let it intimidate you because it's not as bad as you think. So once again, like, share, subscribe, leave a comment. This is Alpha Mad Scientist. Hope this helps.